Marco, are you in the audience? I didn't see you. I see you 20 minutes ago, but I lose you. Ah, okay, you're here. Oh, da, 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 da. So I try to.
I invited him to the stage. There we go.
Yeah, okay, thank you. No? Ah.
Hello?
Hello, Marco. Mark, sorry, I'm misspelling your name constantly. So you are with the Barnard College, and we will have a presentation on human-in-the-loop program synthesis for live coding. I think you can share your screen.
Okay.
Good.
You guys, everyone can see this, I guess.
Yes, great.
Okay, wonderful. Well, thank you for the introduction. Yes, I'll talk about human-in-loop program synthesis for live coding. Lots of different topics today at Farm, so that's very exciting. Okay, so I'm going to start off by with a demo, actually, and I'm going to show 3 different ways to make a drum beat. So let's see if this actually works. Let me know if you can hear this. Can I get some thumbs up, maybe, if the audio is going through? Yes. Oh, okay. I see no.
I don't hear any audio, no.
Okay.
Okay, it seems that we hurt you, but not the system.
I see. Okay, just in that case, perhaps I need to.
Yes, there is a suggestion to pipe your output through your microphone. So perhaps the easiest way is to direct the output of the system on the speakers of your laptop.
Okay. There's no.
Ah, we have lost you too.
Hello? Am I here or no?
No, we hurt you, but not the drum machine.
Okay. Well, I guess we'll have to skip the sound, unfortunately.
Yeah. You are able to listen your own sound?
I can hear my own sound, but I'm not quite sure how to get it over to you.
Okay. You may have to do it without headphones so that we
Yes.
pick up the speakers with your microphone.
I see. Let's see. What if I do this? Is this any good?
Not so much.
Okay. I'll just skip the sound, unfortunately. That's okay. I think the message comes across even if you don't hear it. Right. What I have here is I could construct a drum beat, which you could hear if the sound was working. And what I'm doing here is I'm just selecting notes that I want on or off and their durations with these black circles. So the black circles tell me how long the beat should be, and the gray circles tell me how loud the beat should be. So this is a drum machine, and this is sort of a classic way of creating a drum beat, and this is fine. But if I wanted to create a more complicated beat, let's say I wanted every odd beat, then I have to go through and I click on all of these, which is a bit tedious. So instead, what I would like to do is be able to, well, I look at this and I say, hey, I know how to do this in code. This is a very easy program to write. So I'm going to just do live coding. And so this is the equivalent version of how we could also do this. This is a different way of doing this. And I'll start from, well, let me start from here. So I could have a live coding view. And in a live coding view, I would do some programming here. And if this was all working, I could do something like this, and I'm going to get that same pattern that I mentioned before, and you would be able to hear this. So these are two different ways. We've have drum machines, which are, you know, an old-fashioned sort of way. They're still very popular, but a very manual way of constructing beats. And then we have our live coding, which is a new sort of popular way of constructing live performances. But what are the downsides here? So if we go here, with the drum machine, we have a very accessible interface. You point and click, and it's very easy. With live coding, one of the issues, you're getting a lot more expressive power, but the issue is that it's a less accessible interface. You need to actually know how to code. So this is where live coding plus synthesis enters. So you sort of briefly saw this. If I turn on both of these views, I can now start to construct patterns through this interface. But at the same time, as I click through this interface, code is being synthesized that corresponds to what I'm writing here. And I can change this code, and accordingly, the well, this is also going to change, right? And so I can do all sorts of different things here. Well, let's do that, and maybe. And so I can get different patterns appearing here. So I still have access to my live coding interface, and then I also have access to my interactive clicking interface. And this is powered by program synthesis. So it's a little more exciting when you can hear things, but if anybody, if you want to try it out while we're looking at it, you can go to this link, and there's a live demo, so you can get a sense. So this is sort of the human in the loop aspect of this. We have our coding interface where we can do live coding. And we can also do some sort of initial synthesis where we're clicking on these beats manually. And that will generate code, and then we can edit the code, and that will change the beats that we have. And then we can still change the beats through the GUI interface, and that's going to do some program repair and fix up the program to meet the specification of the new buttons down here. So this is following, for those of you that saw Ravi's keynote at the beginning of ICFP, which is very cool. This is following this sort of intersection of PL and HCI, and how we can sort of enable interesting program, the expressive power of programming, while also having the more accessible interface of some sort of direct manipulation. So I'm going to walk through how exactly this works. So the most magical part of this, is when we're clicking on these beats, and we're suddenly getting formulas here that we're generating code just from clicking on the beat. So we'd like to figure out how exactly does that work. So I'll walk through this. So the first thing that we do is we look at these tracks, and we split each track into an independent synthesis problem. And so we're going to start by looking at just one track, one drum track. And we're going to generate example constraints based on the time indexed and note value. So here we're looking at Tom1, and we have at time index 0, we have a 1. At time index 1, we have a 0, which represents no beat. And time index 1, we have, or time index 2, we then have a 1. So we're encoding this array as a series of input-output examples for a function f. And then we can write down these constraints. This is a language called SYGIS, or syntax-guided synthesis. And this allows us to specify we would like some function that's going to generate this array down here. And these are the examples that we have so far. The other thing we need to do is prune any large subsequences of a common value. So we want to sort of ignore all of these zeros that we haven't clicked on yet, because these are not semantically zeros, they're just items that the user hasn't clicked on yet. So we're going to only look at the range in which the user has actually interacted. And then with this, we can run synthesis, and we're going to get back using a SMT solver to solve these synthesis constraints called CVC4. We then get back a function here, in this case, 1 minus I mod 2. And then what we're going to do is translate this back into a map function over the array that we construct. And this is how we get our result here. So that's how we do our initial synthesis when we're just clicking, but how do we do the program repair? Well, actually, program repair, if we already have code, follows a very similar strategy. So every time we click on a button, we always have a naive fix to the code. So if I were to click on this index 4 right here, then I would immediately get a there's an immediate solution to repairing the current program, which is to have an indexing operation to say, okay, at track 1, index 4, you should put a 1. Now, this is a fine fix. It brings the code and the interface into alignment, but it's not a very useful code for us. So after we generate the naive fix, we're then going to proceed with synthesis as before, where we split it up and generate these constraints. And if we do find a solution, then we're going to replace the naive code fix with the optimized code fix. And this is how we can generate more interesting patterns. There are a number of issues. So I've got a demo. I can't demo it for you, but you guys can try it out. But what I really want to focus on are all of the things that have not been solved yet, which I think are very interesting problems that we've identified. So there's 2 spaces where we have issues. One is algorithmic and one is in the interaction. So the first is, how do we handle state? So here I have a sort of arrow diagram of the way that our system is working. So we have this generate beat function, and this is the function that the user is writing in the code. And then we have user interaction, which induces code changes, either through typing in the code or through program synthesis. And that's going to replace this currently running arrow. So for those of you familiar with arrowized FRP, you can kind of think about this as arrow switch, where this is generating this is a higher order arrow where we're swapping out a new function, or our looping generate beat function here. And this is just manipulating the beat data, which is that array of the drum machine, and sending that to the audio engine at every time step. But this introduces some questions about what the best way to handle certain situations are. So as we have this loop, we need to have some initial value. So our initial value is going to be just, let's pretend an array of all zeros, so none of the beats are turned on. And then we write in the code track 0 should, track 1 at index 0 should get 1. And so now our new state is here. And then we update the code to write track 1 at index 1 also has a 1. And we have our updated code here. We have an array with index 0 and 1 both have 1s. Now what we do is we remove this second line. And the question is, what should be at index 1? Strictly speaking, if we were to look at this as a looping arrow loop, then we would still have a 1 here because we're persisting this state. But it's a bit unclear what exactly purity means in this hot swapping environment. Should this at index 0, should we keep the state that we've previously edited, or should we jump back to our initial state? And part of the question of what is the right answer, I think might have to do with some of the context in which the user has made this change. Was this a change that the user made in the code? If the user has just deleted this from the code, then maybe we want to keep that 1 there, because the user might be preparing to write some sort of generalization of the code. But if it's a GUI edit, if it's a manual edit in the interface, then maybe it's more of a strong signal that this really should be, this state should return to its initial state. Unclear, and a question that I'm looking for feedback on. There's also some race conditions that arise when we have this interactive synthesis setting. Specifically, what happens when synthesis is too slow? So here's a timeline. We have a synthesis request at time step 1, a synthesis request at time step 2, and we only get the response to synthesis request 1 after we've received synthesis request 2. So let's walk through an example. So here we have our specification is in state A, and our code is in state A with the naive fix A to the N. Then we have a synthesis request 2. If we get a new synthesis request, it means our specification, our examples are in a new state, state B, and the code is in state B with the naive fix for B. Now our synthesis responds and says, "Oh, I've got some optimized code for state A. Let me give that back to you." And now we're in this inconsistent state where we have code that matches the functionality of specification A, but we've already moved on to specification B. And then we later get code matching specification B. So the solution here is not so complicated. We can simply only take the response of the most recent request, and we toss out all of these other synthesis responses. The downside to this is that there's lots of wasted computation. And you can imagine if we have a series of synthesis requests, one after another, we're going to be running a number of synthesis requests and throwing away every single response until we stop sending synthesis requests. So this is not an ideal solution exactly. And it gets worse. What if we have synthesis? Synthesis can succeed, but synthesis can also fail. So our synthesis engine may say, you know what, I actually wasn't able to come up with any optimized code for you for specification B. The best you could get is actually specification, the code, the naive fix for B. In that case, we're going to end up in some state where we would like to be able to merge somehow the optimized code from state A, as well as the naive fix for specification B. And this is, again, an open question how this code can be merged together and how we track the responses of successful and failing synthesis responses. Another question more on the interaction side is how do we present synthesized code from a user perspective? Currently, what we do is just overwrite whatever the user has. Ideally, we would do anything except that. It's a bit heavy-handed to simply say, we've come up with a synthesis solution. We think this is optimized code. We're going to delete everything you've written and give you what we think is best. So for more ideas in this direction, see the keynote from the beginning of ICFP, and especially this projection boxes work from Kai in 2020. But this is still a space that we have yet to explore. And another really important question that I think gets more to the heart of live coding is how synthesis actually interacts with the ethos of live coding. So the live code manifesto, available at this link, lists some ideas about what live coding should be. In particular, I think the second point here, obscurantism is dangerous. Code should be seen as well as heard, underlying algorithms viewed as well as their visual outcome. So there's an issue that although synthesis is enabling us, we still see the end code. We don't see the process of synthesis. And to what extent does this interfere with the ethos of live coding? This is still an open question. We have to get the tool in front of more live coders and talk to them about their experience with this. On one hand, it is it does say live coding is not about tools. Algorithms are thought, chainsaws are tools. So the goal here is that synthesis gives you more access to algorithms rather than needing to write everything out manually. It gives you more direct access to the performer's mind rather than watching their fingers type on the keyboard. But at the same time, how much assistance from synthesis is too much? So I don't want to go over time. There's a live demo online. We'll skip the demo that I would do in favor of yourselves. You can also install this locally here. It's a fairly easy install. The version that's running online is running on a expensive server, so I'm only going to keep it up for the next 24 hours or so. It will still be live, but I'm going to downsize the server. The server is what's running the synthesis code, and that requires a bit of processing power, so it's a little expensive to keep it running, at least for me. But you can install it locally, and that also works great. So the next steps are to tackle the aforementioned issues, user testing, and establishing a stronger connection to FRP. I showed that arrowized sort of diagram, but that's very high level and wishy-washy, hand-wavy. So I think that's something that still needs to be worked out. And also connecting this to another synthesis tool that we're working on that you can see at this link here. And I should say that this the most recent version of this tool is also thanks to 3 of my students, Kat, Catherine, and Hannah, who worked over the summer to improve upon the tool from when I had submitted this paper. So lots of the interface improvements are thanks to them. So happy to take any questions. The server is down. Awesome. Okay, well, too many people accessed it, I guess.
Thank you, Mark. Thank you a lot for the presentation. And we will welcome now the question. Don't hesitate to ask one. I have one. And the question is, if I forget a little bit the synthesis, the live coding part, to focus on the programming par example part. It seems to me that, in fact, you learn some relationship between the musical action and some kind of regular word, some kind of word, which is the click on each track. But it seems to me that if I see that as a kind of learning example, it is a well under-specified function. So I suppose that, in fact, you come out with not too much solution because you are looking for a specific kind of relationship. Is it a kind of, I see that you use, for instance, modulus operators. So are you looking for some kind of Pressburger arithmetic to establish a relationship between the tracks and the musical action? Or
Yeah. So sorry, why am I getting an echo? So the examples are an under specification, so there are multiple possible solutions to any examples that we have. And we just sort of, so the tool that we're using, CVC4, will always pick the smallest solution that it can find. And the actual synthesis code is something of a black box using this Cygus SMT solver. So it's encoding the constraints in first order logic, and then using an SMT solver to find a formula that satisfies that first order logic proposition, and then re-encoding that as a program. So there's it's not breaking it down into a Presburger arithmetic. At least I don't think so. It's instead doing whatever these SMT solvers do in the backend, which is quite complicated.
It's quite complicated, but there is a hope to have a formal characterization of what we can represent.
Oh, yes. Yeah. So the way the synthesis works is that we do you specify a grammar. So you specify this is the grammar that you can form programs from, and in terms of what we can represent, it's anything in that grammar. And this will just be an exhaustive search in the worst case, right? You just do a brute force search through the grammar. We do have a timeout though, so
okay.
Right. So it really just comes down to, here's a grammar. Can you find anything within my timeout?
Okay, thank you. Thank you for the answer. Are there some questions from the audience? I think so, and we can...
Yeah, so lots of echoes here with bidirectional transformations. Yes, this is something that is really on my to-do list. It seems to have a lot of and then also Dan is asking about the overlap with machine learning. So there's a lot of different approaches to program synthesis. We have, our SMT solver based program synthesis, bidirectional transformations, which effectively is some sort of program synthesis, and then machine learning. There should be a lot of overlap here. I'm not sure about the bidirectional transformations. That remains to be seen. I assume it would be interesting. For the machine learning, the machine learning is difficult for the beats because that's working over a discrete space, which is a bit hard to map onto a machine learning model. But we also have these sliders, which are over a continuous space. So right now, or my hope is to use some sort of simple regression model just as a proof of concept for modeling the slider behavior.
Okay, there is also a question by Jeremy Gibbons. I think you can read it.
Yeah, I think the answer is yes. And I'm not sure where to go beyond that. I haven't actually worked with bidirectional transformations myself. And I'm not sure what MDE is.
Okay, that's the follow-up of the question. Perhaps, Jeremy, I can invite you on stage to elaborate a little bit the question.
Yeah. Hi. So MDE is model-driven engineering, and there's quite a connection between bidirectional transformation stuff, so people doing lenses in functional programming, but also model-driven development and round tripping and so on. So your purity question comes up in BX as a least change thing. So imagine you've got a UML model and some Java code, and you're trying to keep them in sync. You make a change to one, change happens in the other. You undo the change in one. The smallest consistency fix to put you back might not put you back where you started. It might sort of ratchet you into a different state. The race conditions also come up when somebody's editing the model and somebody else is editing the code, and they don't synchronize while they're doing that. So somehow you have two distinct updates to reconcile. And the preserving layout is also a critical thing. If you're trying to do round tripping between a UML model and Java, you want to keep the code layout and you want to preserve all the comments and things even when they're not reflected in the other half. So I think this is very cool. I mean, I think the synthesis part is very cool, where you try to find a smaller program than just the naive one, but also the connection to BX. I think there's something fruitful there.
Very cool. Thank you. This is a good thing to look into. I always felt like this somehow must have come up many times before in other spaces. So
yeah.
Thank you.
Nice, thank you.
Okay, thank you. If there is no other question, it's the end of the current session. We will take a break of half an hour, and after this half an hour at 3, John will host the performance session, the famous session.
Also, just wanted to mention I got the server back up if anybody does want to click on that link again.
Thank you very much, so we can the result. And yes, okay, so we have a break, and then we start with the performance session. After the performance session, there is another break, and then we have a keynote by Phoenix Perry, and perhaps Phoenix will address some of the question about learning in user interface, and we will see. Thank you, everybody, and see you in half an hour. I remove you from stage, sorry. Okay.
All right, well, we're almost back. Maybe John Leo, if you're ready to go, I could invite you up to the stage. All right.